Video lecture 16D, Calculating the pH of a salt solution. In the previous lecture, we looked at the acid-base nature of salts when dissolved in water. Now we're ready to calculate the pH of solutions that contain weakly acidic or weakly basic salts. This calculation will require an equilibrium calculation, just like calculating the pH of a weak acid or base. In this example, we will calculate the pH of a 0.1 molar solution of sodium hypochlorite. We note that the Ka of hypochlorous acid is 3.0 times 10 to the minus 8. We will need this piece of information later on. Before beginning our problem, we need to determine if sodium hypochlorite is an acidic, basic, or neutral salt. To do that, let's take a look at the ions that make up sodium hypochlorite. That is the sodium ion and hypochlorite ion. The sodium ion is the counter ion of the strong base sodium hydroxide. Therefore, the sodium ion will be a neutral ion. It won't affect the pH of the solution. However, the hypochlorite ion is the conjugate base of the weak acid hypochlorous acid. Therefore, the hypochlorite ion will be a weak base itself. We remember that when we do an equilibrium calculation, we can use our Bike algorithm to set up our calculation. The B in Bike stands for a balanced equation. We'll need a balanced equation for our equilibrium. The balanced equation in this case will be the hydrolysis of the hypochlorite ion. That is, the proton transfer reaction between the hypochlorite ion and water. Since we know that hypochlorite is a weak base, it'll behave as the base in the reaction and accept a proton from water to form hypochlorous acid and the hydroxide ion. The hydroxide ion concentration at equilibrium will allow us to determine the pH. The next step is to create an ice table. Our initial concentration of hypochlorite is 0.1 molar. Before hypochlorite undergoes hydrolysis, we will have no hypochlorous acid or hydroxide ion in solution. Each active species in the equilibrium will change by an increment of x. The hypochlorite ion will change by minus x, and hypochlorous acid and hydroxide will change by plus x. Therefore, at equilibrium, we'll have 0.1 molar minus x for the hypochlorite ion concentration, and x for the hypochlorous acid and hydroxide ion concentration. Our next step is to write a K expression. Since the hypochlorite ion is weakly basic, we will need to write a Kb expression for our balanced reaction. That expression is the ratio between the product between the hypochlorous acid concentration and hydroxide ion concentration and the hypochlorous ion concentration. Before we go on to do our equilibrium calculation, we need some information. We need to know the Kb for the hypochlorite ion concentration. In lecture, we learned that for a conjugate acid-base pair, that the product between Ka for the acid and Kb for the base must have a product that equals Kw. In the problem, we saw that we were given the Ka for hypochlorous acid. Therefore, if we take Kw and divide it by the Ka for hypochlorous acid, we will get the Kb for the hypochlorite ion. This value turns out to be 3.3 times 10 to the minus 7. Another thing we can do is check to see if we can use an approximation. To do that, we need to take the ratio between the initial hypochlorite ion concentration and Kb for hypochlorite. This ratio turns out to be 3.0 times 10 to the 5th, which is much larger than 100. This means when doing our calculation, we can approximate that 0.1 molar minus X is about equal to 0.1 molar, since X will be much smaller than the initial concentration of hypochlorite. Now we are ready to do our equilibrium calculation. Here's our Kb expression again. To do our equilibrium calculation, the E in bike, we will substitute in our Kb value and our initial concentration. Our approximation tells us that we can neglect the X, the change in concentration of hypochlorite. This makes the calculation much simpler. If we solve for X, we find that X is equal to the square root of the product between the initial concentration of hypochlorite and Kb, which turns out to be 1.8 times 10 to the 4th molar. If we look back at our ICE table, we see that X is equal to the concentration of the hydroxide ion. We need to know the concentration of hydroxide to calculate the pH. There are many ways to go about calculating the hydroxide ion concentration from this point. The way we will use is to first calculate the pOH of the solution, which is equal to the negative log of our hydroxide ion concentration. This turns out to be 3.74. To get the pH, we can use the relationship that pH plus pOH is equal to 14. This comes directly from the Kw expression. If we subtract our pOH from 14, we get the pH of the solution, which is 10.26. We should always check to make sure our answer makes sense. It makes sense in a few ways. First, we get a basic pH, a pH above 7. We would expect that for a solution of a weakly basic salt. We also note that our X is much smaller than 0.1. This means that our approximation holds true.